I'm going to speak about how to use geometrical methods to do manifold learning, and then I'm going to apply it to study inverse problems. So the results have been done in collaboration with Charles Pfefferman from Princeton, Sergei Ivanov from Russian Academy of Science in St. Petersburg, Yaroslav Kurilev from University College London, and Hariharan Narayanan from Tata Institute. Oops. So I will first speak about so-called Whitney problem, the classical and geometrical settings, and in practice this means regression. Then we are considering this kind of traditional manifold learning, that is how it is considered in computer science. You have a point cloud, and you want to interpolate it. Then we consider this is in abstract setting when we have abstract manifolds. And then I speak about how the algorithm works and how this is applied for inverse problems. So let me start from the classical, so-called, actually in mathematics we call this Whitney problem, but I think the more applied community speaks usually regression. Let's consider, so in mathematical problem we consider arbitrary set K in Rn. In practice this might be finite number of points, but in principle it could be arbitrary set, which makes this problem mathematically difficult. Then we assume that we are given values of some unknown function in this set K. Like in this picture, the K would be the projection of these data points on x-axis, and at these points we are given the values, so we are basically given these data points. Then we ask that, can we find a smooth function which has m derivatives, such that the maximum of this function f, this interpolated function, minus the values at the data points of function h, is more than epsilon. And also, if this exists, what is the optimal Cm norm? So this is the norm, the maximum of m first derivatives. So in practice, that if you are given these points, how to draw here a curve here which derivatives are bounded, so that it somehow the difference of these data points and the curve is less than epsilon. And up to a constant factor, this was solved by Pfefferman something like within 10 years ago. So now, in this picture, we had a graph of a function. But what if these points here don't form like that? This curve here would not be a graph of a function, but we would have this type of, for instance, this type of Swiss roll surface, points on that, and we would like to find a surface that approximates this. This brings us to a manifold learning problem. And usually in computer science, the manifold learning is taught in the Euclidean space Rd. That we are assuming that we are given a set that we could call data point cloud, like this, all these points here. And we want to somehow find a surface that has lower dimension. So d here is quite large, n would be like lower dimension. And we would like to construct a smooth m-dimensional surface. Here there's actually this Swiss roll surface here, so that it approximates this point cloud, so that the precision, I will somehow soon define what is Hausdorff distance. The Hausdorff distance of the manifold or the surface and the data point is small, and also the curvature of this smooth surface is bounded. And for instance, in this kind of like LIDAR applications where you somehow obtain lots of data points with laser, like for instance, if you would have a statue, would somehow use laser to find lots of points on the statue, and you somehow measure this with cameras from different directions, then you get a point cloud, and you want to somehow form this smooth surface that approximates this point cloud. So this is the first problem that we are going to study. Here we have a submanifold of Euclidean space, but we could consider this in more abstract setting without embedding the manifold to any space. So we could construct an abstract manifold from a metric space. So we could have any metric space, but let us consider now discrete metric space for simplicity. So when you have a discrete metric space, it actually means that you have a graph, you have a finite number of points, and then you know the distances between all these points. So if you are given this kind of finite graph, you ask that when it approximates, in some sense, a smooth manifold. We would like to find a manifold, an abstract manifold. You could consider some n-dimensional surface in some very large dimensional Euclidean space, where you measure distances along the surface. You want to control the curvature of the surface and the injectivity radius. I will come to this in a second. So that the smooth manifold approximates your data set in suitable sense. So what would be an example? If you would have some body in our three-dimensional space, for instance Earth, then we would consider travel time metric. So the travel time metric is the travel time of an acoustic wave from one point of the body to other, from point X to point Y. Now these points could be on the boundary of the domain, or they could be very deep. If, for instance, if Earth, this could be points very somehow deep inside Earth. The travel time defines a non-Euclidean metric that we consider as a distance inside the manifold, and this is given by some Riemannian metric, actually like symmetric tensor, a Riemannian metric, and then we say that the manifold, the body, and this Riemannian metric, they form a Riemannian manifold. So we have a point where we have a source, then it sends acoustic wave, and we ask that at this point, for instance, what is the time, how long time acoustic waves take to go from one point to another point. This defines a non-Euclidean metric that we call travel time metric, and it corresponds to Riemannian distance. So these two problems we are going to study. Let me first start from this more classical problem of computer science that we have point cloud in RD, d-dimensional Euclidean space, and we want to find a surface. So there are many methods to study this. So if we have just a point of j points in Euclidean space, maybe the simplest ones is the principal component analysis, where you just try to find a good n-dimensional plane that fits to the data. There are also this kind of this multidimensional scaling methods, where you try to find in a lower dimensional space, you try to find you could somehow try to embed all the points in n-dimensional space, so that you solve this type of minimization problem. You try to find points that would somehow fit to the data points. A very popular method is to find a manifold, is to define the use the eigenmap algorithm, where you take a graph Laplacian, you construct its eigenfunctions, and then you map points to the values of these eigenfunctions. And this gives an embedding of the manifold basically to lower dimensional space. So this is dimensional reduction. And there is also a long tradition to use neural networks, especially these kind of self-organizing maps, to somehow do dimensional reduction. But now we consider a little bit different methods that takes motivation from Riemannian geometry. And I emphasize that in this talk I now use small deterministic error. We are working on random errors, but this work is ongoing. So now we have errors that are somehow small and deterministic. So when we consider now the difference between a smooth surface and some point cloud, we need to define in what sense we define the difference between two sets. The Hausdorff distance if you have some background space, this could be like d-dimensional Euclidean space. If you have there two subsets, A and B, then somehow the distance between these two subsets, the Hausdorff distance, is given by maximum of the two following quantities. Here are supremums that you could consider also maximums. They are practically the same thing. So this is the maximal distance of points in set A to set B. And this is the symmetric somehow like quantity. So like in this picture, if we have this like these two sets here, then their Hausdorff distance is the distance of this point to this other set. So in this picture, this here is somehow the maximal distance that points in one set have to other set. And we are going to use this to measure the distance between two sets. We also say that the set A is epsilon dense in a larger set Y. If the epsilon neighborhood, this U epsilon A of set A is sorry. So if the epsilon neighborhood of the set is in set Y is this Y. So this basically means now that for every point in Y, there is some point in set A, so that the distance from point Y to this point of set A is less than epsilon. So every point, so the epsilon neighborhood of set A is the whole space. Then we say that space A is epsilon dense in Y. So now when we ask the question that when we are given a point cloud, when it is possible to somehow find a surface that approximates it. We are going to use the following condition. Now we consider Euclidean space E, that could be this space RD. And I denote by this, I denote balls with radius R and center X in set E, like this. So surfaces they locally look like flat. You could somehow consider that when you have a surface, every point has a tangent plane that approximates it well. Motivated by this, we say that the set X in this large dimensional Euclidean space is delta close to n flats at scale R. So delta and R are just small parameters. If the following is true, that I take any point X in this point cloud, but we require that there exists some affine plane, n-dimensional plane, that goes through X, so that if I consider the if the intersection of the point cloud X with ball of radius R centered at X, and the intersection of plane with the same ball, that the Hausdorff distance of these two sets is less than delta. So, for instance, like that near this point here, when I consider a ball around or near it, then the points are close to lower dimensional plane. Like in this picture, the planes are one-dimensional lines. So in this ball, all points are like close to lower dimensional plane. And in this region, all these points are close to lower dimensional plane. And we note that if we have a priori we have some smooth n-dimensional surface in Euclidean space, then it is like if when r goes to 0, then it is CR squared close to n flats in scale R. So this power R2 squared here is important. And what is our result? It is that if we consider if this could be an infinite dimensional case that we have separable Hilbert space or large dimensional Euclidean space. If I consider a fixed dimension of the surface that I'm considering, I somehow consider R and delta, where delta is small enough. Then if the point cloud in this Euclidean space or Hilbert space is delta close to n flats at scale R, then there exists some either a somehow closed, like bounded surface, or infinite surface, that complete surface, that is n-dimensional smooth submanifold, so that the Hausdorff distance of the point cloud and the constructed surface M is bounded by 5 times delta. Then also the second fundamental form that measures the curvature of the surface. This is at every point of the surface, it's bounded by constant times this quantity delta r to power minus 2, and also the normal injectivity radius, that is the neighborhood where you can extend the tubular coordinates around this surface, is bounded. So when this result is useful, it is useful when this curvature bound here is finite. So if you choose parameters so that this, for instance, the delta is smaller than CR squared, then this here is bounded quantity. And the surface that we somehow construct has bounded curvature. And up to a constant factor, this is optimal. Why is that? Because if we somehow a priori start from a surface, we know that the surface is CR squared close to n flats in scale R. So if we take a surface and we take points from there, apply algorithm given by the proof of this theorem, it gives us a surface that has bounded curvature. So it is actually has the same curve. It actually will have the same curvature as the original surface multiplied by a constant factor. So in this sense, this result is optimal. Let me explain how this construction of this smooth surface somehow goes. Here's a picture that somehow that gives the proof and also gives the construction. This actually good proofs give always construction algorithms. So if you have this kind of point cloud that approximates here some surface, so this point cloud is these black points, and they are in this between these two blue lines. Then we take this area and we squeeze. I'll give this more precise definition in a second. We squeeze it in this area, so that here it is squeezed to follow a plane, and here it's somehow like we squeeze it softly to get this type of set. Then we take this area, we squeeze it. Then we take this area, we squeeze it there. We produce a smooth surface. So let's see how this somehow is done precisely. So let us for simplicity assume that we are considering a case when this parameter r is 1, and that we have a finite point cloud in d-dimensional space. And let us assume that this set x happens to be delta close to n flats at scale r. Then we implement the following steps. First, we take a very sparse sub point cloud. We take maximal set of points in this set x that are separated by 100. Then in this sparse net, we take point, and we know that each point it is close to n flat in scale r. So there are some affine planes, so that locally near the point qi in this sparse net, the point cloud is close to some affine subspace. So let us consider an orthogonal projector that maps all points to this affine plane. So let's go to the picture. So we somehow near this point, we know that there exist many planes. Let's take one of these planes, or here these lines, that some approximates this point cloud more or less well. And let's consider orthogonal projector to this plane. Then we take a cutoff function, a smooth function that is close, that is equal to 1 near 0, and then goes smoothly to 0. And using this cutoff function, we take a convex combination of the orthogonal projector and the identity operator. So this is a squeezing operator that locally squeezes everything to the plane. When this cutoff function is 1, then this is just an orthonormal projector, but then it smoothly transforms in the space to identity map. So this is local squeezing, and then we combine all these squeezing maps. So here was this squeezing map that is a combination of orthogonal projector, convex combination of orthogonal projector and identity map. So here it is exactly the projector, here it is somehow like, here far away it is identity map, and here it is convex combination. So here we have a local squeezing map. And then we squeeze this point cloud everywhere, and we obtain a surface that is actually smooth n-dimensional surface. So combining all the smoothing maps, sorry, we take a delta neighborhood of the point cloud and we squeeze that. So this blue region actually is squeezed locally everywhere. This gives us an n-dimensional surface that satisfies this condition, and up to a constant factor, it is optimal. So now we will use this to a little bit more abstract setting. Let me recall this problem B here that we now. So what I have spoken now was that in this first problem, where we have a point cloud in RD, d-dimensional Euclidean space, and we want to find a surface. Now we apply this result in abstract setting. We take some metric space that is actually a discrete graph in practice, and we want to somehow ask that how you can find an abstract manifold that approximates it. And I promise to say a few words about this injectivity radius. The injectivity radius, if you would have a point source somewhere in the domain, it sends a wave. The injectivity radius is in practice, that is the distance to the caustic, where the waves produced by point sources have caustics. So we want to bound that also. So let us go to the problem of learning an abstract manifold. We are given a discrete metric space, just the points with distances, and we want to construct some abstract surface in some Euclidean space where the distances measured along the surface approximate the distances that we are given in our data, when we are given a discrete metric space. Again, we have to somehow compare now two metric spaces. We have to compare the data metric space that is given for us and the smooth manifold that we want to construct. So there's a concept of Gromov-Hausdorff distance. Here is somehow like a fancy mathematical definition, which says that if you have two compact metric spaces, then their Gromov-Hausdorff distance is defined in such a way that we take the infimum or the minimum of the construction where we take arbitrary metric space, we embed both these metric spaces that we are given x and y isometrically to a larger metric space, and then we consider the Hausdorff distance in this larger metric space. So this is a very beautiful and elegant mathematical definition, but there's also a more practical definition. That is that we say that Gromov-Hausdorff distance of two metric spaces is the minimum or infimum of the following of all epsilons for which the following is true. That if we have here one metric space, we take their epsilon dense net. Then we have other metric space and we take their other epsilon dense net. And then we number these points. This is numbered like 1, this is 2. Here is 1 and 2. Then we compare distances here between the numbered points, here and here. If the distances in metric space x and distances in metric space y between the numbered points have only epsilon error, and somehow these discrete nets were epsilon dense nets, then we say that the Gromov-Hausdorff distance is smaller than this epsilon. And if we take minimal epsilon, or the limit of infimum of all epsilons for which this is true. So we ask that can we somehow put there discrete approximations of these objects so that we make epsilon errors. This is what practically this Gromov-Hausdorff distance means. Now to construct abstract manifolds, we need two conditions. We need a local condition and we need a global condition. The local condition is just that this, like the manifolds have tangent planes, so it looks locally like a flat object. So this here denotes the ball in the metric space x of radius r and center x, and this is the balls in Rn. So we then say that metric space, and we have the parameters r and delta. We say that the metric space is delta close to Euclidean space Rn at scale r if the Gromov-Hausdorff distances of the balls in the metric space and the balls in the Euclidean space is smaller than delta. So if you have a manifold, then the manifold is close to its tangent space locally. And we note that a compact smooth manifold is actually C to power R3 close to Rn at scale R. Here it's interesting that its power here is actually better than in earlier. So actually the smooth manifolds are very close to flat spaces in this sense. So this is the local condition. Then we need also a global condition. The global condition that we use is a good generalization of so-called Hopf-Freedom theorem, which says that any 2 points can be connected by a geodesic. Geodesics are like locally shortest curve. So any 2 points can be connected on a manifold can be connected with the length minimizing curve. Now we have a discrete metric space, so we need a discrete analogy of this condition. So when delta is a given parameter, we say that we have a sequence of points is delta chain. If the distances of this point like x1 to x2, from x2 to x3 and so on, if they are less than delta. Then we say that a sequence is delta straight, so it approximates like a distance minimizing curve, approximates in Euclidean space, it approximates a line. If for all I, j, and k, like sum of these distances is less than like this distance plus delta. So it means that if you want to go from here to here, for instance, we could go from this point to this middle point, and from this middle point to here. And if this road from here to here, and plus distance from here to here, is less than distance from the start point to the end point plus delta, then we say that this is delta straight. And finally, we say that a metric space is delta intrinsic if any 2 points can be connected with delta chain that is delta straight. So up to delta errors, any 2 points can be connected with discrete geodesic that is straight up to error delta. So this is the global condition that we need. And this is our main theorem, which says that if we have any metric space of bounded diameter, we have specified what dimension we are looking, then we somehow look the scale and some error in distances. If we know that this metric space is delta intrinsic and it is delta close, so this is the global condition, and local condition is valid that it is delta close to flat space Rn at scale R, then there exists the n-dimensional smooth manifold, so that the Gromov-Hausdorff distance of the discrete metric space and the smooth manifold is bounded by this quantity. The sectional curvature of the manifold is bounded by this quantity, and also injectivity radius is bounded. And this result is interesting if you use parameter delta that is order CR to power 3, because then here we have a constant, and here we have something that is small. So this actually tells now that when we have a metric space, when we can approximate the metric space with a smooth manifold. And because of this, let me go back here, that all smooth manifolds were CR to power 3 close to Rn at scale R. This also says that this result is optimal up to a constant factor. So instead of having a point cloud in some like large dimensional space, we can just take an abstract somehow metric space, a graph, and we can ask that when we can interpolate it to a smooth surface. When from local distances and global, when from distances we can learn an abstract manifold. So geophysically, this would mean that if we would somehow inside Earth measure from some different points travel times of acoustic waves, then we could somehow obtain a smooth approximation for the wave speed inside Earth. Here's actually a corollary that is interesting for inverse problems. So there are actually 2 corollaries. One would be actually that we give a characterization for metric spaces that are close to manifolds. But that is related to metric geometry, and I don't go to that. There's more somehow concrete which says that if we a priori have some compact manifold with bounded curvature, and we take sufficiently small r and use parameter that is this curvature bound times r to power 3, and injectivity radius has some bound. Then if we take any somehow discrete set in the manifold that is delta dense in the original manifold n, and if we are given these local distances with errors. The local distances with error is any function that for small distances it's equal to the distance plus small error, and for large distances it can be anything. Then, so if you have given just like discrete this kind of approximation of the smooth manifold and this local distance function with errors, then we can construct a compact n-dimensional Riemannian manifold, so that the manifold that we construct is diffeomorphic to the original manifold. The distances satisfy this type of Lipschitz condition from above and below, where L here is close to 1. So distances have very small somehow like deformations, multiplicative deformations. Also the curvature is the same as the curvature of the original manifold multiplied by an absolute constant, and also the injectivity radius of the manifold changes only very little bit. So this basically means that discrete approximation, if you somehow like measure distances in a somehow discrete set, in finitely many points, then this means that actually we can obtain the smooth structure. There's an abstract interpolation that gives the metric tensor. Let me explain the contraction algorithm shortly related to this last theorem. So here is the picture that I will explain in a second. So here we have this kind of discrete metric space, these red dots. And locally we know that they are approximate Euclidean space. So we can have here pieces of Euclidean space, so that locally the metric space approximates disks or balls in Euclidean space. Then we will embed all these disks to large dimensional Euclidean space, these blue curves. And we consider that these blue curves are the point cloud in the Euclidean space. Then we apply our first result. We construct this red smooth surface that approximates this point cloud, and we obtain find an orthonormal projector to this surface that we then use to construct the metric. Let me explain this more rigorously. Again, assume that we are given parameter r is equal to 1, and we have a finite metric space. And roughly the idea of the algorithm is the following. We first select from the data space, this discrete metric space, a coarse or sparse subnet that is 100 separated. Then we know that locally, there are all these points in this subnet. There are some Euclidean balls, so that there is an almost isometric map from the ball of the metric space to this like these balls in Euclidean space. So let me go here. So here we had this our abstract metric space. Locally, we can take here balls on the metric space, embed them, map them to Euclidean space, so that we make small errors. Now, okay, then we consider transition maps. We consider these disks as local coordinate charts. Then there are transition maps between the local coordinate charts that can be chosen to be affine. So that we make small, there are transition maps with small errors. So let me go back to here. So here when two balls in the metric space intersection. So we say that this coordinate chart and this coordinate chart, they are glued together somewhere here and here. And there is a like linear map that glues them together. Now we have lots of somehow these kind of flat pieces. We want to glue them together. And we use so-called Whitney embedding. We take smooth cutoff functions that are 1 near 0 and embed and take union of all these disks that we constructed. And then we embed this disks, we define first maps that map these disks to n+1 dimensional space, so that the last component here is something that actually is 1 close to the center of the disk and 0 elsewhere. And then here we have this same indicator function times affine embedding. So this is not so important actually if you are not familiar with Whitney embedding, but this means that we somehow we have maps from the disks to n+1 dimensional space. And then we glue them together. We take sequence of these maps. This is takes inspiration from called Whitney embeddings, how manifolds are embedded to some Euclidean space. And the disks are embedded in this way to a large dimensional Euclidean space. These here are now considered as a point cloud in this large dimensional Euclidean space. And we use this first result, this first algorithm that we used for the point clouds to find a smooth surface and construct a normal project of this surface. So let's go back to the picture. So we somehow embedded first these balls to Euclidean space. They could be glued together. These glued coordinate charts are embedded to large dimensional Euclidean space, this union of these blue curves. And then these blue curves are considered as a point cloud in Euclidean space. They are interpolated in Euclidean space to smooth submanifold. And we obtain also a metric tensor. Sorry, we obtain an orthonormal projector. Then the metric tensor is constructed by taking the Euclidean metric here. Then we push it forward first to these blue curves, so that these are like images of Euclidean space. Then we push them forward to the surface and glue them together by using smooth partition of unity. And this gives the metric tensor on this abstract manifold. So that is basically the construction that gives the surface in some large Euclidean space and a metric on it. And this is, like I said, this is optimal up to a constant factor. So how to apply this now for inverse problems? Okay, let us consider a wave equation. I consider this M here could be now a model of Earth, for instance. I consider acoustic wave equation with some wave speed that I denote by G. So here is actually the Laplace-Beltrán operator. It is a little bit modified anisotropic wave operator. We consider waves that have vanishing initial data and Neumann boundary conditions, so that the normal derivative of the solution is F. So physically this would be acoustic wave, and I think this is the pressure, some kind of boundary source causing pressure. Okay, I denote by U UF, a wave produced by this source F. And then we define the Neumann to Dirichlet map that maps the boundary source to the Dirichlet boundary value of the solution. This is the map that maps basically the boundary source to the boundary value of the source. This would be, in geophysics, it would be the measurements done on the surface of Earth. And our boundary data is the boundary that we are given, and this Neumann to Dirichlet map. And we asked that how we can find the metric inside the manifold. And we are going to use so-called boundary control method developed by like Berdichev and Kurilev, somehow early results, and Tatarov's unique continuation result. That was defined in Euclidean for Euclidean scalar wave operators on these years, and later then to the manifolds. I didn't emphasize there are also partial data results by myself and Lauri Oksanen. And here I'm going to somehow consider point, somehow cloud, so we are actually interested of focusing waves to points. And I want to emphasize that there are like now very recently like very efficient like numerical constructions by Dehoop, Kepley, and Oksanen. And also we are going to use some kind of reconstruction of metric from point source data that we somehow developed by like De Hoop, Holman, Iversen, and Ursin, and also with Teemu Saksala, who is actually now starting postdoc here in RISE. And also that actually Lauri Oksanen will speak about this kind of like how to formulate this type of measurements, not on the boundary, but for interior measurements, and consider the relationships to passive measurements with white noise source later in this conference. So, let me recall this. We are considering wave equation with boundary measurements where boundary source is mapped to boundary value of the wave. How to connect this kind of boundary information to something that is related to the interior of the manifold. There is so-called Bloga-Wejczynski identity. If you consider the L2 inner product of waves at given time moment t, so we integrate only over the x variable, then there is an explicit formula which says that what is the L2 inner product, this integral, of two waves in terms of the boundary operator, this Neumann to Dirichlet map, time reversal operation, and a filter. And by using this, we can use so-called modified time reversal iteration. Yeah, that is somehow like resembles. I know in geophysics and also in medical imaging, people use a lot of time reversal. And so, okay, here was this Bloga-Wejczynski formula that says that inner product of waves can be computed by using boundary data. We can modify this, consider there are three boundary sources, F, H, and P, and consider the differences of different waves and their time derivatives. Add some regularization terms. And this type of functional, this kind of quadratic form that resembles energy, the actual difference of the energy of difference of waves. This can be also computed from boundary information very similarly. And with Dahl and Kirpichnikova, we showed that by using so-called modified time reversal iteration, we can actually find boundary sources that solve the following blind control problem, that they focus waves at given time to a single point. We somehow have difficulty to say what the point is because we don't know the metric, but we can use ray coordinates. We can take the boundary point, Z, and go along the ray to normal direction, deep into the Earth, distance S. So in these ray coordinates, we have a point Y, which ray coordinates are Z and Y. And at this point, we can focus the wave. In medical imaging, this kind of idea is used to somehow for medical treatments by focusing the energy of ultrasonic waves to single point. And also here are actually some of the simulations in the University of Eastern Finland related to this. And this is actually nowadays used even in somehow in the medical use in hospitals, where they somehow call this bloodless surgery, where they focus waves to kill tumors. So how this is related? We can now focus waves to single points. So we can, if we somehow focus waves so that at time t is equal to capital T, they are focused to single point. If we wait a little bit longer, then we see that from this point, what is the travel time from interior point to here? So we basically get, with some errors, this approximative. With small errors, we get the distances from interior points to boundary points. And with Katsuda and Kurlev, we showed that if we somehow know the set of all these kind of interior to boundary distance functions up to a small error, then we can reconstruct the distances inside the manifold up to other error that has Hölder somehow stability related to this error here. And these results can be now combined together to get stability estimates to inverse problems. So basically, we somehow used focusing of waves to construct the point cloud inside the Earth. And then we use this type of result to construct the travel times between 2 points inside the Earth. and then we smoothly interpolate it to get the smooth wave speed everywhere. But thank you for your interest.